NASA went to Jupiter to study a storm everyone thought they already understood, and found something much more disturbing. The Great Red Spot looked familiar from a distance, but the closer NASA got, the more it turned into a mystery that kept breaking the old story apart. And if you like watching space-related videos, make sure to subscribe to the channel. Let's begin. For a long time, the easy version of the story was too simple. People saw the Great Red Spot as a giant red swirl, something fixed on Jupiter's surface, almost like a permanent feature painted onto the planet. But that is not what it is. Jupiter does not even have a solid surface like Earth. The Great Red Spot is an active anticyclonic storm system in Jupiter's atmosphere, centered near 22 degrees south latitude. And NASA's data made that clear in a way older observations never could. Once Hubble and Juno started measuring the storm properly, scientists were no longer just describing how it looked. They were measuring how wide it is, how deep it goes, how fast it moves, how its winds are arranged, how it drifts, and how it changes over time. That is the first important shift in this story. A famous object in space is one thing. A storm you can map in 3D is something else. Once NASA could treat the Great Red Spot as a physical system instead of just a visual landmark, the whole conversation changed. It stopped being a symbol of Jupiter and started becoming a machine inside Jupiter's atmosphere. So what was the first big surprise? Because this is where NASA's answer got much more serious than people expected. For years, one reasonable assumption was that the Great Red Spot might be mostly a cloud-top event. In other words, it might look dramatic from above but stay relatively shallow compared with the deeper layers of Jupiter's atmosphere. That would have made sense. Telescopes mostly showed the upper cloud deck, the visible top of the storm, so the easy idea was that the red oval might be intense, but mostly confined to the upper atmosphere. Juno changed that. NASA's measurements showed that the Great Red Spot reaches roughly 350 to 500 kilometers below the visible cloud tops, or about 220 to 300 miles. That is not a small correction. That is a major change in how you describe the storm. A shallow weather feature does not reach that far down. A storm with roots hundreds of kilometers deep is a large atmospheric engine. NASA compared that depth to Earth in a very direct way. The Great Red Spot extends around 50 to 100 times deeper than Earth's oceans. That single comparison is enough to break most of the normal weather analogies people like to use, and that is where the scale starts to become hard to ignore, because the depth is only part of the story. The Great Red Spot has also changed dramatically in width over time. In the late 1800s, astronomers estimated its long axis at about 41,000 kilometers, around 25,500 miles. That made it enormous even by Jupiter standards. Then Voyager measured it at 23,300 kilometers, or 14,500 miles, in 1979. By April 2017, NASA measured it at 16,350 kilometers, about 10,159 miles. That means the storm has been shrinking for a very long time. It is still huge, still about 1.3 times the width of Earth, but the long-term trend is obvious. The Great Red Spot is not fixed. It is changing. That is one of the reasons NASA's findings hit so hard. This is not just a giant storm sitting there unchanged for centuries. It is a giant storm that evolves. Even in its smaller modern state, winds in the surrounding high-speed ring reach about 560 kilometers per hour, roughly 350 miles per hour. So the storm is shrinking, but it is still extremely powerful. It is changing shape, changing size, and still staying organized. That leads to the next important point. People usually expect a simple story from a storm. If it gets smaller, then it must just be fading. If it has lasted a long time, then it must be stable. If it looks familiar, then it must be easy to describe. NASA's data does not support any of those easy conclusions. The Great Red Spot can shrink, change geometry, and still remain active. That means the old idea that large storms simply decay in a slow, straightforward way does not really fit what scientists are seeing here. So what does fit? Because that is where this story becomes more interesting. NASA found signs that the Great Red Spot behaves like a dynamic system, balancing several things at once. It is shaped by Jupiter's rapid rotation. It interacts with surrounding jet streams. It depends on deep atmospheric structure, not just the upper clouds. It has temperature differences between levels, and later sections of this story make clear that chemistry matters too. In simple terms, this storm is not surviving because it is frozen in place. It is surviving because it is actively maintained by the environment around it and below it. That is why the phrase big storm is no longer enough. A big storm could still be shallow, simple, and slowly dying. The Great Red Spot is not that. NASA found a storm that is deep enough to be measured by gravity effects, large enough to dominate a region of Jupiter, and changeable enough to force scientists to keep revising their models. It is not a decorative red oval, it is an ongoing physical process, and that changes the tone of the entire video, because from this point on, the Great Red Spot is no longer just something you recognize from a Jupiter poster. It becomes evidence. It becomes a test case for how weather works on a giant planet. Once Juno and Hubble turned it into something measurable, every new result started adding pressure to the old story. The storm is deeper than expected. It is shrinking but not disappearing. It stays organized while changing in ways that should make that harder. That is why NASA did not just confirm what people already believed. NASA made the storm more difficult to explain. So the core claim for this entire video is very simple. NASA found that the Great Red Spot is deeper, less stable, more physically complex, and probably more dynamic than people used to think. It is not just surviving on Jupiter, it is exposing the real behavior of giant planet weather. And every time scientists get better data, the storm becomes less familiar and more serious as a scientific problem. And once that became clear, the next step was obvious. Scientists had to stop relying on distant views and go straight over the storm itself. That is where the story gets much more precise and much more difficult to ignore. Juno changed the story the moment NASA stopped looking at the Great Red Spot from far away, because until that flyby, even the best science still depended too much on distance. In July 2017, Juno did something no spacecraft had ever done before. It flew directly over the Great Red Spot for the first close-up scientific pass. At closest approach, it was only about 9,000 kilometers above the storm's cloud tops, about 5,600 miles. That is close enough to completely change the way you talk about this storm. This was not a distant image of Jupiter with a red oval on it. This was a direct pass over the largest storm in the solar system, and the approach itself matters because the geometry tells you how serious this was. About 11 minutes earlier, Juno had crossed another 39,771 kilometers, around 24,713 miles, as it dropped deeper through Jupiter's environment on the way in. So this was not a slow hover, and it was not a long observation from safety. It was a fast, tightly timed pass through one of the harshest planetary environments in the solar system, aimed straight over a storm that had already survived for generations. NASA was not just taking a better picture, it was making a direct measurement run through a planetary weather system. So why did that matter so much? Because you could say telescopes had already shown the Great Red Spot for decades. The answer is that telescopes mostly showed the top. They gave shape, colour, movement across the face of Jupiter, and some information about cloud motion, but they could not fully tell you what was happening below the visible cloud deck. The flyby changed that, because Juno was not designed to be just a camera with some science attached to it. It was built to measure Jupiter from multiple physical angles at once. That is the next thing people miss when they hear about this pass. Juno was not there to take one dramatic photo and leave. NASA had all the 8 science instruments active during that flyby, along with Juno Cam. That is important because the Great Red Spot is not a single-layer object. If you only use visible light, you mostly learn where the top clouds are and how they look. But the storm is deeper than that, hotter in some levels than others, and more massive than it appears from the outside. So NASA had to hit it with different kinds of measurements at the same time. Visible imaging shows cloud patterns. Infrared helps with temperature and composition. Microwave measurements probe below the visible cloud tops. Gravity science tells you where mass is sitting underneath. When you put those together, you stop treating the Great Red Spot as something you simply observe and start treating it as something you diagnose. That is why this flyby was such a turning point. Juno did not just look at the storm, it tested it. And out of all those tools, one of the biggest game changers was Juno's microwave radiometer, or MWR, because that instrument helped NASA get below the part of the storm human eyes can actually see. That's a major shift in the whole story. Ordinary telescopes mostly stop at the upper cloud decks because they depend on light bouncing off the visible tops. For most of history, that meant the Great Red Spot was measured mainly at its surface appearance. You could see the red oval, you could track its sense, you could estimate wind speeds from cloud motion, but you were still mostly studying the top layer. Juno's microwave system changed that by peering progressively deeper beneath the visible clouds through 6 channels designed to sample different depths. That is why microwave vision mattered so much. It pushed below the visual ceiling and showed that the storm's large-scale structure continues much deeper than older observations could directly confirm. NASA also noted that Juno's microwave methods can probe down toward pressures of about 100 bars, roughly 100 times Earth's sea level pressure. That does not mean Juno could see straight to the center of Jupiter, and it does not mean the Great Red Spot is an open shaft down into the planet. What it does mean is that scientists could finally study how the storm connects to deeper atmospheric layers instead of guessing from the top down. So the Great Red Spot stopped being just a cloud problem and became a pressure-structured atmospheric problem. Then the flyby added something even more serious, because Juno was not only reading the storm's thermal and microwave structure, it was also detecting how the storm's mass affected the spacecraft itself. This is where gravity science changed the tone of the entire discussion. Juno's radio link was precise enough that tiny changes in the spacecraft's motion could reveal details about the distribution of mass below it. That is how NASA constrained the depth of the Great Red Spot to roughly 350 to 500 kilometers below the cloud tops, about 220 to 300 miles. That result matters for a very simple reason. A storm that can slightly tug a passing spacecraft is not just a visual pattern in the clouds. It has enough organized mass below the visible level to produce a measurable gravitational signal. That is a completely different level of reality. At that point, the Great Red Spot is no longer just weather in the loose sense people use that word. It becomes a deep physical structure inside Jupiter's atmosphere. It still is weather technically, but now it is weather with enough depth and internal organization to show up in gravity data. That is why the flyby was such a break with the old story. Before this, the Great Red Spot was famous. After this, it was measurable in depth, in structure, and in mass distribution. And that creates a much harder set of questions, because once NASA proved the storm is physically deep, the mystery got sharper, not easier. If the Great Red Spot reaches hundreds of kilometers below the cloud tops, what keeps it organized for so long? If it has been shrinking for decades, why do some winds seem to increase instead of simply fading? If the red color is shaped by sunlight and upper atmosphere chemistry, then what exactly is the deeper atmosphere doing underneath that visible layer? The flyby did not settle those questions. It made them unavoidable. That is why this moment matters so much in the script. Before Juno, the Great Red Spot was one of the most recognized features in planetary science. After Juno, it became one of the best measured storms in the solar system. NASA did not solve it in one pass, but it did something almost as important. It turned a famous mystery into a physical one. Now scientists were no longer asking only what the storm looks like. They were asking what it is built from, how far down it goes, how it is powered, and how it keeps changing without falling apart. And once you can ask those questions, the next problem gets much more serious, because the flyby proved the roots of the storm go far deeper than they were supposed to. The Great Red Spot was supposed to be easier than this, because from far away, a wide storm can still be shallow, and for a long time that was one of the safest assumptions scientists could make. That assumption is now gone. Before Juno, it was reasonable to think the visible red oval might be mostly an upper atmosphere feature. Not fake, not small, not unimportant, just shallow compared with the full depth of Jupiter. That would have fit the old picture. You see a dramatic cloud pattern, you measure the top, and you assume the deeper atmosphere is doing something broader underneath, while the red storm is mostly riding above it. But Juno's results forced NASA to drop that idea. The Great Red Spot is not just spread out across the top of Jupiter's cloud layer. It penetrates well below the visible clouds, down to about 350 to 500 kilometers, or around 220 to 300 miles. That number needs to land clearly, because on Jupiter, even a few hundred kilometers is a very serious depth for weather. It is still less than 1% of Jupiter's radius, so this is not a storm that goes all the way into the deep interior of the planet. But that does not make it small. For atmospheric science, that depth is enormous. On Earth, storms do not extend hundreds of kilometers down into a hydrogen-helium atmosphere, because Earth is not built like Jupiter. Earth has a solid surface, a completely different atmospheric structure, and weather systems that operate under very different limits. Jupiter gives storms a completely different environment to grow in, and the Great Red Spot is one of the clearest examples of that. So this is where the Earth comparison matters, because it helps you feel the number, instead of just hearing it. 500 kilometers is the precise scientific figure. 300 miles is the body feel version. 300 miles is the kind of distance people actually know. That is the kind of distance you drive between major cities in the United States. It is not a tiny correction hidden in the data. It is the difference between a storm that sits on top of clouds and a storm that reaches far down into the atmosphere below them. NASA's own comparison makes the point even harder. The Great Red Spot extends about 50 to 100 times deeper than Earth's oceans. That is the point where the hurricane analogy breaks. People like to compare the Great Red Spot to a hurricane because both are storms, both rotate, both have powerful winds, and both look organized from above. But once you bring in depth, the comparison stops helping. Hurricanes do not have roots hundreds of kilometers deep inside a giant planet. Hurricane eye walls do not extend anything close to that far. A hurricane is a severe weather system in Earth's atmosphere. The Great Red Spot is a deep vortex inside a gas giant. Those are not the same category of object, and Juno's data made that impossible to ignore. So then the next question becomes more important than the width, because width is the part everyone notices first. But width is not what changed the science most. A storm can be very wide and still be fragile. It can spread out across the top of an atmosphere and still be mostly superficial. Width tells you scale, but not structure. Depth tells you whether the storm is actually connected to the atmosphere below it. That is why Juno's microwave and gravity results were so important. They showed that the Great Red Spot is mechanically tied to deeper circulation, at least through several hundred kilometers of vertical extent. That means the visible red oval is not the whole storm. It is the upper signature of a system that continues downward, carrying momentum, heat, pressure differences, and chemical structure below the cloud tops that human eyes can see. That changes the whole language of the story. Now the Great Red Spot is not just a red shape, it is a vertically developed vortex. It is not just a top layer being moved around by something else underneath. The storm itself is part of the deeper atmospheric flow. The red cloud tops are the visible part, but they are not the whole object. Once you know that, the storm becomes harder to simplify. The top is connected to the lower structure. The winds are connected to depth. The chemistry at the top exists above a much larger atmospheric system. There is another important part here, because NASA did not find an infinitely deep storm. That limit matters just as much as the depth itself. The Great Red Spot is deep, but it is not bottomless. The best current constraint is a few hundred kilometers, not thousands. That rules out two easy mistakes at once. First, it is too deep to be dismissed as a surface-level cloud effect. Second, it is too shallow to be treated as a direct opening into Jupiter's deepest interior. This is not a weather stain on the top of the atmosphere, but it is also not a direct pipe into the metallic hydrogen regions deep inside the planet. And that actually makes it more interesting, because it puts the storm in a narrow physical regime, where weather starts to overlap with interior dynamics without fully becoming deep planetary structure. In simple language, it lives in the middle zone where atmospheric science stops being simple weather and starts becoming something larger. That is why this result matters so much. It gives scientists a stronger range for the storm's real size in 3 dimensions, and that forces models to become more specific. You cannot just say it is shallow anymore. You also cannot say it extends endlessly downward. The storm has real roots, and those roots have a measured scale. That is the first major point in this whole story where the older picture clearly fails. NASA found that the Great Red Spot is not a shallow red mark sitting on Jupiter's cloud tops. It is a layered atmospheric structure with vertical development, measurable depth, and enough organized mass below the visible clouds to show up in microwave data and even in the way it perturbs a passing spacecraft. That result alone rewrites how you talk about the storm. It is no longer enough to describe what it looks like. Now you have to describe what it is connected to. And once you accept that the storm has roots, the next problem becomes harder, because depth by itself is not the whole answer. A storm can be deep and still be physically simple. The Great Red Spot is not simple either. Because NASA found something else under the clouds, the storm is cold at the top, warmer below, and that changes what powers it. The Great Red Spot is not just deep, it is built in layers, and one of the most important layers is temperature, because NASA found that the storm is colder at the top and warmer below, and that helps explain why its winds are so extreme. That sounds simple at first, but it changes the whole physical picture. Once Juno showed that the Great Red Spot is not a shallow feature, the next question was obvious: what is happening inside that depth? NASA's answer made the storm harder to simplify. The Juno team reported that the Great Red Spot is warmer at its base than at its top. That matters because temperature differences are tied directly to motion in an atmosphere. In other words, the storm's internal heat structure is part of the reason its winds behave the way they do. Andy Ingersoll, speaking about NASA's results, put it very clearly. The warmth at the base helps explain the intense winds at the top. That is a major shift in how you describe the storm. It is not just a rotating patch of gas that happens to look violent. Its vertical temperature structure is connected to its flow. The storm is being supported from below, not just spinning at the cloud tops for visual effect. That is where the physics becomes more serious, because once temperature is part of the engine, the Great Red Spot stops looking like a single-layer weather feature. And this was not completely invisible before Juno. Long before the flyby, infrared observations had already shown that the cloud tops of the Great Red Spot are unusually high and cold compared with nearby parts of Jupiter. Older thermal maps from JPL showed the center of the storm appearing colder than the surrounding atmosphere at the 500 millibar level. On Earth, that pressure level is roughly comparable to about 6,000 meters or 20,000 feet above sea level. That colder signature made sense if the Great Red Spot had raised cloud tops sitting higher in the atmosphere. So even before Juno, scientists already knew the top of the storm had a distinct thermal signature. The problem was that this could still lead people to oversimplify the system. If the top looks cold, then the easy mistake is to imagine the whole storm as basically cold. NASA's later results made it clear that this is wrong. The Great Red Spot does not have one simple temperature identity. It has vertical thermal structure. The top is cold, the deeper part is warmer, and that contrast is part of how the storm works. That is the point where the hurricane comparison fails again. On Earth, people think about storms in a familiar way. Warm water, rising air, clouds, rotation, rain bands, pressure gradients. Even when the science is complex, the general setting still makes intuitive sense because we live inside that kind of atmosphere. Jupiter does not work like that. The Great Red Spot sits in a stratified gas giant atmosphere with no solid ground underneath it. Different pressure layers, different chemistry, and much deeper circulation. So when NASA says the top is cold and the base is warmer, that is not a small detail. It means the storm is organized vertically in a way that has no clean, everyday analogy. The visible clouds are only tracing the upper part of the object. The real system extends downward into layers where pressure, temperature, and motion all change with depth. That is why calling it a giant hurricane is not enough. The Great Red Spot is much closer to a rotating atmospheric system, whose visible top hides a deeper thermal structure that helps keep the whole circulation going. So why does that matter so much? Because a temperature difference on its own does not sound dramatic until you connect it directly to the winds. NASA did exactly that. The Juno results link the storm's winds to temperature differences inside the vortex. That means the Great Red Spot's extreme wind speeds are not just a dramatic surface feature. They are part of a thermodynamic structure. The temperature gradient from warmer below to colder above helps maintain the circulation. In simple language, the storm's internal heat arrangement helps support the way the storm moves. That is why this is not just a visual story anymore. A picture can show you red clouds, a giant oval, and bands around Jupiter. But a picture cannot tell you why the winds stay that strong, or why the storm keeps its shape, or how the upper and lower layers are connected. For that, you need real atmospheric physics. You need to know what is warm, what is cold, what is high, what is deep, and how those differences feed the flow. Once NASA showed that the Great Red Spot is warmer at the base than at the top, the storm became more than a deep vortex. It became a thermally organized system. Its cold upper cloud region is not the whole story. Its deeper, warmer structure is part of the engine that helps sustain the top-level winds. And that is the main point of this section. NASA found that the Great Red Spot is not only deep in shape, it is also structured in temperature. The storm has a cold cap and a warmer lower region, and that thermal contrast helps power its circulation. Once you know that, the old image of the Great Red Spot as a giant red swirl becomes too simple. It is a layered atmospheric system with depth, pressure structure, and internal heat differences that matter directly to how it moves. And that makes the next part even more unsettling, because once you understand the storm is deep and thermally organized, the obvious question is whether it is at least stable. NASA's answer to that was no, because even while this system stays alive, it has been shrinking in plain sight. The Great Red Spot is getting smaller, and that should have made the story easier, but it did not, because the more NASA measured the shrinkage, the less the storm behaved like something simply dying. The numbers are the first thing that makes this impossible to ignore. In the late 1800s, the Great Red Spot's long axis was estimated at about 41,000 kilometers, or 25,500 miles. That is an enormous storm by any standard. Then Voyager 1 and Voyager 2 measured it at about 23,300 kilometers, around 14,500 miles in 1979. By April 2017, NASA measured it at 16,350 kilometers, or 10,159 miles. That is still huge, still about 1.3 times the width of Earth, but the trend is clear, without any extra drama. Over more than a century, one of the most famous storms in the solar system has been shrinking. That alone would already be a major result. A storm this iconic is often treated like a permanent object, something fixed in the public imagination. But the measured record says otherwise. The Great Red Spot is not the same size it used to be. It has been losing width for generations. It is still big enough to dominate the conversation about Jupiter's atmosphere, but it is no longer the enormous stretched oval that older observations showed. Then the story got more serious because the shrinkage did not stay slow and steady. NASA's Hubble monitoring added another important detail. Around 20 to 12 observers saw the rate of shrinkage increase noticeably by about 580 miles per year. That is a rate people can actually understand. A storm that covers a region larger than Earth should not feel fragile, and yet NASA was tracking a vortex that was losing span at a pace that becomes obvious over only a few years. It was not just changing on long historical timescales anymore. It was changing fast enough for modern monitoring programs to watch it happen. And the shape was changing too, not just the size. The Great Red Spot had long been known as a stretched oval, but as it shrank it also became rounder. It started shifting away from that longer elliptical shape towards something closer to a circle. That matters because shape is part of the storm's physics. If the geometry changes, then the internal balance of the vortex is changing too. So the Great Red Spot is not simply contracting like an image being scaled down. It is reorganizing its form while it shrinks. That is where the expected story starts to fail. If a storm gets smaller, the easy assumption is that it must be weakening in a simple way. You expect it to lose energy, smooth out, slow down, and gradually collapse. That would be the clean explanation. But NASA's later Hubble results did not support that clean version. Even while the storm has been shrinking overall, the outer high-speed ring has shown acceleration. Other observations also showed that the storm can oscillate and deform rather than just fade in a straight line. That is why a smaller Great Red Spot is not a simpler Great Red Spot. The shrinkage does not mean the system is becoming easier to explain. In some ways, it becomes harder. A storm that gets smaller while parts of its wind field speed up is not following the basic script people expect. It suggests the storm is becoming more concentrated, or at least redistributing its energy in a more complicated way than simple weakening. So NASA was not watching a giant vortex quietly die. NASA was watching a storm change state. Then another twist made the picture even stranger. In 2018, NASA's Hubble results suggested that as the Great Red Spot shrinks in length, it may also be getting taller. The storm was described as only large enough now to fit just over one Earth across. But cloud property measurements suggested the vortex was becoming more vertically pronounced as its horizontal footprint contracted. That is a very important detail, because it rules out the lazy explanation that the storm is just evaporating away. If the footprint gets smaller while the vertical structure becomes more pronounced, then the storm is not simply disappearing. It is reorganizing. It is changing how its mass and energy are distributed. In plain language, it may be becoming more compact in one direction while standing out more in another. That is not what a straightforward collapse looks like. That is what an evolving system looks like. So this section lands on a much harder conclusion than people expect. NASA found a storm that has clearly been shrinking for generations. The numbers leave no doubt about that. But the shrinkage did not produce the clean decay story scientists might have wanted. Instead, the Great Red Spot became rounder, showed changing wind behavior, and may have become more vertically pronounced as it contracted. That means the storm is not just fading in a simple, predictable way, it is changing form while staying alive. And that raises the next problem, because once a shrinking storm starts getting faster in some places, the real question becomes even sharper. Why are the outer winds speeding up while the centre follows different rules? The Great Red Spot is getting smaller, but some of its winds are getting faster, and that is one of the clearest signs that this storm is not fading in any simple way. That result came from Hubble's long-term tracking, and it is exactly the kind of finding that breaks the easy version of the story. Researchers found that the average wind speed in the Great Red Spot's high-speed outer ring increased by as much as 8% from 2009 to 2020. That is the outermost fast-moving lane just inside the storm's boundary, the part where the circulation is already extreme. So now the picture becomes much less comfortable. You have a storm that has clearly been shrinking over time, but instead of just slowing down as it contracts, part of it is speeding up. That matters because the normal expectation would be the opposite. If a storm loses size, most people assume it is losing strength in a broad, straightforward way. They expect it to calm down, become less intense, and move toward collapse. But NASA's measurements did not show that. The edge of the storm got faster. So the Great Red Spot did not become easier to explain as it got smaller. It became more complicated. And the next point is just as important, because that speed increase was not happening everywhere in the same way. NASA made it clear that the Great Red Spot is not behaving like a rigid spinning disk where every part of the storm changes together. The later Hubble summaries showed that the outer winds are speeding up while motion toward the centre is much slower. That means the storm has internal zones that follow different rules. The edge and the core are not evolving in lockstep, they are responding differently over time. That is a major clue about the real structure of the vortex. From far away, the Great Red Spot looks like one object, one oval, one giant rotating storm. But once you measure it carefully over years, that simple picture starts to fall apart. The edge has one behavior, the center has another. The speed is not uniform, the evolution is not uniform. This is not one flat rotating surface wall. It is a differentiated vortex with internal structure. That is one of the most important patterns in NASA's findings. Every time the storm looks simple from a distance, the data shows it is more layered than it appears. First, the depth was more serious than expected. Then the temperature structure turned out to be more complicated than expected. Now the wind field is doing the same thing. The Great Red Spot is not one single behavior repeated across the whole storm. It is a system with different zones, and those zones can change independently. So why does an 8% increase matter so much? Because on paper that number can sound modest until you place it in the real context of the storm. The Great Red Spot's outer ring is already moving at around 560 kilometers per hour, about 350 miles per hour. An 8% increase on top of that is not a small adjustment. It is a serious dynamical change in a storm that was already extreme. NASA compared it to a driver in the outer lane picking up speed, and that comparison works because it captures the pattern clearly. The outside lane is moving faster while the inner parts are not matching that same change. And the way NASA found this matters too. This was not the kind of result you get from one dramatic flyby or one beautiful image. It came from patient, repeated observation over more than a decade. Hubble's long baseline made it possible to detect a trend that would be invisible in snapshots. If you looked only once, or even only a few times, you might still think of the Great Red Spot as basically constant. But when you measure it year after year, the drift in wind behavior becomes visible. That is a very important lesson in this whole story. Some of the biggest discoveries about Jupiter do not come from one close pass. They come from watching the same object over time until the pattern stops hiding. Then NASA added another layer to the problem, because it was not just the outer winds that changed. The storm's rotation story changed too. Hubble's decade-long monitoring through the Opal program found that the Great Red Spot's rotation period is shortening as the storm evolves. That means the timing of the circulation is changing, along with the storm's size and its edge winds. So now the list is getting harder to dismiss. The storm is shrinking, the outer ring is accelerating, the center is not matching that same trend, and the time it takes the storm to rotate through its circulation is changing too. At that point, the Great Red Spot stops sounding like a stable object that is only slowly wearing down. It starts sounding like an evolving dynamical system, adjusting its internal balance. And that is the real tension in this section. If the size is changing, the edge winds are changing, and the rotation period is changing, then what exactly is the stable part of this storm? That is the question NASA's results force on you. The Great Red Spot clearly persists. It has not fallen apart. It is still one of the most recognizable and long-lived storms in the solar system. But persistence is not the same thing as stability. The storm keeps its identity while its internal behavior shifts. So by this point, the contradiction should be clear. The Great Red Spot is smaller than it used to be, but that does not mean it is weakening in one clean direction. Its outer winds have sped up, its rotation behavior has changed, its center and edge are not evolving the same way. So NASA did not find a storm that is simply fading. NASA found a storm that is actively redistributing its internal balance, and that is much harder to explain than a simple decline. And the next section makes that even harder, because once Hubble watched the storm closely enough over a short period, it found something even more disruptive. The Great Red Spot is not stable in shape either. The Great Red Spot looks permanent, but Hubble showed that even its shape is moving, and that may be one of the most unsettling results in this whole story. In 2024, NASA and the Space Telescope Science Institute reported that Hubble watched the Great Red Spot over 90 days, from December 2023 to March 2024, and found that the storm is not as stable as it appears. The comparison NASA used was simple and very hard to forget. The storm jiggles like a bowl of gelatin. That line stands out because it sounds almost casual, but but it came from real measurements, not from style or exaggeration. Hubble was tracking the changing geometry of the storm over a full oscillation cycle, and the result was clear. The Great Red Spot does not just sit there in one fixed shape. Even its outline shifts over time. That matters because the Great Red Spot became famous partly because it looks permanent. It is one of those features people assume is always there in the same basic form. From far away, it feels stable enough to act like a landmark on Jupiter. But Hubble's close monitoring showed that this confidence is misleading. The storm keeps its identity, yes, but its shape is not locked in place. It changes, and it changes on a timescale short enough to watch directly. And this was not a case of one strange image or one odd day in the data. Hubble tracked the storm's size, shape, brightness, colour, and vorticity through that full cycle. That is what makes the result so important. NASA was not reacting to a visual impression, it was measuring a pattern. The Great Red Spot became slightly skinnier, then slightly fatter, while still remaining the same overall storm. It did not break apart, it did not vanish, it oscillated. That is a very different kind of finding from simple shrinkage. Shrinkage is a long-term trend. Oscillation means the storm is also moving through shorter cycles in its own geometry. So now the Great Red Spot is not just changing across decades, it is also changing across months. The closer NASA watches, the less static this storm becomes. That is why this result hits so hard. Planetary scientists have observed the Great Red Spot continuously for about 150 years in the modern era, and the historical story around it goes back even further if you include earlier possible sightings. A storm with that kind of reputation is supposed to be the steady reference point. It is supposed to be the thing you compare other Jovian weather to. But Hubble's 90-day campaign showed that even this benchmark is flexible. Even this storm is moving through a cycle that forces a big correction in how people think about the data. Once you know the Great Red Spot oscillates, every measurement of its size, its brightness, and even the exact position of its edge becomes harder to interpret in isolation. A single snapshot is no longer enough. You have to ask where the storm is in its cycle when that measurement was taken. Was it in a slightly stretched phase, a slightly compressed phase, a brighter phase, a dimmer phase? That means older models may have treated the storm as steadier than it really is. And that creates a much deeper scientific problem, because an oscillating storm is harder to model than a rigid one. If the Great Red Spot's outline, brightness, and vorticity shift through a measurable cycle, then scientists need models that do more than reproduce its average shape. They need models that reproduce the breathing motion too. That is a tougher task. A vortex that survives for generations but changes shape over a few months is balancing persistence and flexibility at the same time. It keeps its overall identity, but it does not keep one exact geometry. That tells you something important about the environment around it. The Great Red Spot is not isolated. It sits between powerful jet streams inside a turbulent atmospheric system with internal layering and changing wind behaviour already visible in the data. So the wobble makes sense as part of a broader balance. The storm is stable enough to survive, but not so stable that it becomes rigid. It is being shaped by its surroundings while still resisting collapse. That is why the oscillation matters. It is evidence that the storm is alive as a dynamical system, not fixed as a permanent mark. So this is the clean shatter point for the section. NASA found that the solar system's most famous storm is not sitting on Jupiter like a fixed target. It is pulsing, it is deforming, it is moving through measurable oscillation cycles over just 3 months. The Great Red Spot is ancient in human terms, but in atmospheric terms it is active, flexible, and still changing. And that leads directly into the next tension point, because once a storm is wobbling at the same time it is shrinking, the obvious question is whether its edges are starting to fail too, and NASA found signs that the borders are under stress. The Great Red Spot is not just changing from the inside, it is also being worked on from the outside, and one of the clearest signs of that is that parts of its edge have been seen peeling away while the storm itself kept going. That is a very strange thing to say about a storm this large, but NASA highlighted exactly that. JPL reported that the Great Red Spot has been observed shedding slivers of red material from its western edge. This flaking was described as a recent recurring phenomenon, first seen in ground-based observations in 2017. And that result matters immediately, because the first reaction most people have is simple. If a storm is flaking apart, then maybe it is finally collapsing. That sounds reasonable, but that is not what happened. The storm kept going. So now the contradiction gets sharper. The Great Red Spot can appear to lose visible material at the edge and still survive. It can look like it is peeling apart in one area without simply falling apart as a whole. That forces a more careful way of thinking about the storm. Its boundary is active, its outline is not fixed, and visible changes at the edge do not automatically mean the entire vortex is about to die. That becomes easier to understand once you stop treating the Great Red Spot like an isolated object. NASA's Hubble reporting had already pointed in that direction years earlier. In 2014, astronomers noticed very small eddies interacting with the storm, and they suggested those smaller features might be connected to the accelerated shrinkage by altering the Great Red Spot's internal dynamics and energy balance. That is an important clue, because it changes the story from the storm is just weakening to the storm is being affected by the atmosphere around it. That is a much richer picture. The Great Red Spot is enormous, but Jupiter's atmosphere is also full of motion. Smaller vortices, local disturbances, and nearby turbulent structures do not just sit around it harmlessly. They can feed into it, distort it, and change the way it behaves. So even the biggest storm in the solar system is not sitting in calm isolation. It is part of a larger traffic system, and that traffic matters. That is the broader lesson of this whole section. The Great Red Spot is not a sealed system. It lives between powerful east-west jet streams, inside a banded atmosphere filled with vortices, waves, and shear. Its borders are under constant pressure from the environment around it. That means the red fragments, the changing outline, the wobble, and the ongoing shrinkage are not just internal signs of decay. They are signs of interaction. This is why border events matter so much. They show that the Great Red Spot is not only managing its own internal structure, it is also negotiating with its surroundings all the time. The edge is where that negotiation becomes visible. When red material appears to peel off, it tells you that the storm's boundary is not a hard wall. It is a moving interface between the vortex and the rest of Jupiter's atmosphere. And that is exactly why the obvious interpretation turned out to be too simple. When people first heard about the flaking, it was easy to jump to a dramatic conclusion. Maybe the Great Red Spot was entering its final stage. Maybe it was breaking down and would disappear within a few decades. But the science has stayed more cautious than that. Some researchers have argued that the apparent flaking may reflect interactions with other vortices or changing cloud coverage, rather than direct destruction of the deep vortex itself. That distinction is very important. The visible red pieces at the edge do not necessarily tell you that the whole storm underneath is being destroyed in the same way. The outer appearance can change because of cloud level interactions, edge disturbances, or local atmospheric effects, while the deeper vortex remains intact. Once again, NASA found that what the Great Red Spot looks like on the outside is not always a simple guide to what is happening underneath. That has now become a pattern in this entire story. The storm looks simpler from a distance than it really is. It looks like a red oval, but it is deep. It looks steady, but it oscillates. It looks like it is shrinking, but some winds speed up. It looks like it is flaking apart, but that does not automatically mean the whole system is collapsing. Every time the storm gives you an easy visual story, the physics makes that story harder. So the conclusion here is very clear. The Great Red Spot is not just shrinking from within, it is also being shaped from the outside. Its edge is a zone of conflict. The storm is being fed, squeezed, distorted, and sometimes visibly stripped by the surrounding atmosphere. That makes its survival more impressive, not less, because it means this vortex is not persisting in calm conditions, it is persisting while under pressure. And once the audience understands that the border is active, the next question becomes unavoidable. Because if the edge can be stripped and the deep vortex can still survive, then what exactly is making the storm red in the first place? and NASA's answer was far less mysterious than people expected. The Great Red Spot is famous because it is red, but the red colour is not just a look, it is part of the science, and NASA's leading explanation is much more specific than the old popular story. For a long time, people treated the colour almost like a mystery stain, as if something deep inside Jupiter might be pushing red material upward from below. That idea sounds dramatic, but NASA's research points in a different direction. JPL described the leading explanation in a very direct way. The red colour is probably more like a sunburn than some deep internal bleed. In simple terms, the reddish material is likely produced when ordinary chemicals in Jupiter's upper atmosphere are changed by sunlight. That matters because it moves the origin of the colour upward. Instead of needing some strange hidden source deep inside the planet, the modern picture says the colour can form in the upper atmosphere through photochemistry. That means sunlight is part of the story. The Great Red Spot is not just red because of what it is made of, it is red because of what happens to those ingredients when they are exposed to the right conditions high above the cloud tops. That is where the chemistry starts to become more precise. One of the leading NASA-linked ideas is that ammonia, after being broken apart by sunlight, can interact with acetylene and produce a blue-absorbing chromophore. A chromophore is just the part of a material that gives it colour by absorbing certain wavelengths of light. In this case, the haze would absorb more of the shorter blue wavelengths, which makes the Great Red Spot appear redder to us. That is a big shift in how you think about the storm's colour. It means the redness may not come from some exotic deep substance rising out of Jupiter's interior. It may come from common atmospheric ingredients being processed in an uncommon environment. The ingredients themselves are not the shocking part. The shocking part is the setting. Jupiter gives you the right pressure, the right altitude, the right sunlight exposure, and the right chemical mixing for those ingredients to produce a reddish haze. And that leads to the next important point, because the Great Red Spot is not just any part of Jupiter's atmosphere, its height matters. NASA's Goddard explanation emphasized that the Great Red Spot's clouds sit high, and that changes the chemistry. A higher cloud structure means greater exposure to sunlight and better access to the upper atmosphere conditions where this kind of photochemical processing can happen. If the red chromophore forms most effectively where ammonia reaches higher levels and interacts with sunlight and hydrocarbons like acetylene, then the storm's altitude becomes part of the reason it looks the way it does. That is a very clean result, because it ties appearance directly to physics. The Great Red Spot is not simply a vortex that happens to be red. Its vertical structure may help produce the red colour in the first place, so now the colour is not a separate mystery floating on top of the dynamics. It is connected to the storm's structure, its altitude, and the chemistry happening above the clouds. That makes the story stronger, because it means the visible colour is telling you something real about the storm's environment. And the chemical picture has become more detailed in newer work too. Later studies using JWST and related data moved the explanation beyond vague ideas about some unknown pigment. NASA's records tied the colour story more closely to ammonia distribution, cloud structure, and the continued support for a chromophore-bearing haze above the storm. In other words, the modern view is layered. Below you have cloud structure and condensation. Above you have reactive chemistry and haze formation. The red colour may be the topmost visible result of how those layers interact. That is important because it keeps matching the same pattern we have seen in every section so far. The Great Red Spot looks simple from a distance, but every closer measurement reveals layers. The shape is not simple, the winds are not simple, the depth is not simple, and now the colour is not simple either. The visible red top is part of a stack of processes, not a single isolated feature. So this is one of the biggest correction points in the whole video. The old popular idea was that the Great Red Spot might be red because something deep and mysterious was rising up from inside Jupiter. NASA's leading interpretation is less mythical and much more convincing. The red colour is probably a product of sunlight acting on atmospheric ingredients that have been lifted into the right place. The storm is not only a dynamical system, it is also a chemical system. And once you accept that, the next question gets deeper again. Because if the red haze is only the uppermost visible layer, then what is sitting underneath it? And NASA found that below the red top there is a whole stack of clouds and volatile chemicals. The red top is the part people remember, but NASA found that below that visible layer, the Great Red Spot sits inside a much deeper stack of clouds and volatile chemicals, and that changes the storm from a single red feature into a full atmospheric structure. Once the colour story points upward to sunlight and photochemistry, the next question naturally goes downward. What is underneath that red haze? NASA's records point to something much more structured than a simple cloud deck. Spectral studies found an opaque cloud inside the Great Red Spot at about 5 plus or minus 1 bars of pressure, and the most likely interpretation is that this cloud is water. That is a major result. On Jupiter, water clouds sit deeper than the ammonia cloud tops most people usually hear about. So this means the Great Red Spot is not just spinning above some vague lower atmosphere. It connects to a deeper cloud architecture that includes water. That matters because water is a serious ingredient in giant planet meteorology. Once water enters the picture, you're no longer talking only about the visible upper clouds. You're talking about a storm linked to deeper layers with their own chemistry, condensation and structure. That is where the image of the Great Red Spot has to change again. From a distance, it looks like one red oval. In reality, NASA's broader picture of Jupiter's atmosphere is layered. The upper atmosphere includes ammonia-related clouds. Below that, there are ammonium hydrosulfide clouds, and deeper still, there are water clouds. So the Great Red Spot's visible red cap sits on top of a chemically stratified atmosphere. It is not one cloud, it is not one layer. It is part of a sacked system, and once you combine that with Juno's microwave data and infrared spectral work, the whole storm becomes much more three-dimensional. At the top you have hazes and the red chromophore-bearing material shaped by sunlight and upper atmosphere chemistry. Below that you have ammonia-related cloud layers and atmospheric structure that affect the storm's visible appearance. Deeper down you have the likely water cloud layer. So the Great Red Spot is not just a vortex on top of clouds. It is a vortex moving through a vertical set of cloud and pressure layers. It is a cloud system inside a vortex system. That is why chemistry and dynamics keep showing up together in this story. The storm's motion is not separate from what the atmosphere is made of. The layers matter physically. Ammonia is one of the clearest examples of that. NASA linked records tied to the 2024 JWS T-related study note that ammonia distribution, compared with the cloud distribution, suggests that ammonia may condense into thick cloud layers over the Great Red Spot. That is important because it connects composition directly to what the storm looks like and how its upper structure behaves. Ammonia is not just background gas, it helps build cloud decks, and those cloud decks are part of the storm's visible and physical structure. So once again, the same pattern appears. The Great Red Spot looks simple from far away, but as soon as NASA starts measuring it properly, everything splits into layers. The storm's shape has layers, the wind behaviour has layers, the temperature has layers, and now the cloud chemistry has layers too. That is also where Juno's microwave radiometer becomes important again, because this is exactly the kind of problem it was built to attack. Ordinary images stop at the visible tops. The microwave radiometer can probe much deeper, down toward pressures of about 100 bars, roughly 100 times Earth's surface pressure. That does not mean Juno can see the Great Red Spot like an open vertical tunnel all the way down, but it does mean scientists can start inferring how volatiles like ammonia and water are arranged below the level where visible light stops being useful. And on a gas giant, that is a big change in how you talk about altitude. On Earth, people think in terms of height above the ground. On Jupiter, the atmosphere is so deep in layers that altitude often has to be described in terms of pressure levels instead. Juno helped make that shift possible for the Great Red Spot. It turned the storm from something that looked like a painted red object into something organised by pressure, chemistry and depth. That is the scientific payoff of this whole section. NASA found that beneath the famous red cloud tops there is a structured atmospheric stack involving ammonia, deeper water clouds and pressure-defined layers that influence how the storm behaves. The Great Red Spot is not just red clouds spinning in place. It is a multi-layer vortex embedded in a chemically stratified giant planet atmosphere. And once you understand that the storm is sitting inside this kind of layered environment, the next question becomes even bigger. Because how does a storm this deep, this layered, and this physically stressed survive for so long on a planet that should seem violent enough to tear it apart? The Great Red Spot survived for so long not because Jupiter is gentle, but because Jupiter removes some of the limits that kill storms on Earth, and at the same time gives them a much larger and more violent system to lock into. The first part of that answer is simple, and NASA states it very directly. Jupiter does not have a solid surface in the way Earth does. That matters more than most people realize. On Earth, storms lose energy through friction with land, through interaction with continents, coastlines, mountain ranges, and surface differences that break up circulation. Even over the ocean, Earth's storms still live inside a much thinner and more constrained atmospheric system. Jupiter removes almost all of that familiar logic. There are no continents to tear a storm apart, no mountain ranges to disrupt it, no solid ground to drag against it and bleed off its motion. That means a vortex can keep its angular momentum for much longer than your Earth-trained instincts would expect. So right away, Jupiter gives the Great Red Spot one huge advantage. It does not have to survive contact with the kind of surface that destroys major storms on Earth. But that is only the first part, because a planet with no solid surface could still have a chaotic atmosphere that tears storms apart anyway. Jupiter does have chaos, but it is the kind of chaos that can also organize very large structures. That is where the planet's rotation becomes critical. A day on Jupiter is only about 9.9 hours long. That is extremely fast for a planet that large. Fast rotation strengthens Coriolis effects, and those effects help organize powerful jet streams and major vortices. NASA notes that Jupiter is crossed by more than a dozen prevailing winds, with some equatorial winds reaching up to 539 kilometers per hour, or 335 miles per hour. So the Great Red Spot is not sitting in a calm atmosphere. It sits inside a high-energy system of belts, zones, and fast-moving flows. That sounds like it should make the storm less stable, and in one sense it does. Jupiter's atmosphere is violent, but the same fast rotation that makes it violent also helps create structure. The jet streams are not random. The bands are not random. The whole planet is organized into lanes of motion, and the Great Red Spot exists inside that larger framework. So Jupiter's rotation does two things at once. It creates a dangerous environment, and it creates the conditions that can support giant, long-lived vortices. That is why the Great Red Spot is not just surviving because it is big, it is surviving because it is sitting in the right place. The storm lives between major east-west jet streams, and that confinement is one of the keys to its longevity. The surrounding jet environment helps trap it, shape it, and maintain it. In simple language, the Great Red Spot is not drifting freely through a featureless atmosphere. It is sitting in a specific dynamical lane on Jupiter. The belts and zones around it matter. The neighbouring winds matter. The storm is being held in a region where its circulation can persist instead of immediately being torn apart. That is a much better explanation than just saying it is huge. A giant storm can still die if the surrounding atmosphere does not support it. The Great Red Spot lasts because it is embedded in a system that can sustain giant vortices. It has deep roots, strong rotation, no solid surface below, and a surrounding jet structure that helps confine it. That is the real combination. Size matters, but the environment matters more. And there is another point here that makes the story better, because long-lived does not mean fixed. NASA notes that the Great Red Spot drifts westward and circles the planet in roughly 4.5 years. So this storm is not glued to one point on Jupiter. It persists, but it also moves. It migrates, it changes size, it changes shape, and it changes internally while still remaining the same overall storm. That is an important distinction. Longevity on Jupiter is not the kind of permanence people usually imagine. The Great Red Spot is not surviving because it is frozen in place. It is surviving because it is dynamically maintained while staying in motion. That fits everything NASA has found so far. The storm can endure for generations and still not be stable in the ordinary sense. It can survive for centuries and still shrink. It can remain recognizable and still wobble. It can keep its identity and still shed material at the edges. So the real lesson is not that Jupiter allows perfect stability. The lesson is that Jupiter allows persistent instability. It allows a storm to stay alive for an extremely long time while still evolving the entire time. That is the clean conclusion for this section. The Great Red Spot lasted so long not because Jupiter is calmer than Earth, but because Jupiter is built differently. No solid surface, rapid rotation, deep atmospheric layering, powerful jet streams, and planetary scale. All combine to create a regime where a giant vortex can survive for centuries. But NASA's newer findings add the part that makes this much more interesting. Surviving that long does not make the storm simple or steady. It can persist and still wobble, shrink, speed up at the edges, and shed material. That is the real shock. Longevity did not mean the Great Red Spot was a static object. It meant Jupiter had found a way to keep a changing system alive. And once you understand that, the next step is bigger than the storm itself, because NASA eventually stopped treating the Great Red Spot as just something to explain and started using it as a way to probe Jupiter's whole atmosphere. The Great Red Spot stopped being just a mystery NASA wanted to explain and became something even more useful, a way to study Jupiter's whole atmosphere through one storm. That is one of the biggest changes in the story. At first, the Great Red Spot looks like a special case, almost like a side feature on Jupiter that gets attention because it is large and easy to recognize. But Juno's science changed that view. By 2021, NASA was describing the mission as giving the first real 3D view of Jupiter's atmosphere, and that work did not just include the Great Red Spot by itself. It included the belts, the zones, the polar cyclones, and the broader atmospheric structure of the planet. That means the Great Red Spot is not a side exhibit, it is part of the map, and once it becomes part of the map, the role of the storm changes. NASA was no longer just asking, what is this storm? NASA was also asking, what can this storm tell us about Jupiter as a whole? Its depth matters not only because it is surprising, but because it gives clues about how deep atmospheric flows on Jupiter can go more generally. Its temperature structure matters not only because it helps explain the storm's winds, but because it shows how heat and motion are connected inside a gas giant atmosphere. Its chemistry matters not only because it explains the red colour, but because it reveals how cloud layers, sunlight and atmospheric mixing work together on Jupiter. That is why the Great Red Spot became more than an object, it became a diagnostic window. This storm is especially valuable because it is large enough, long-lived enough, and active enough to be studied in multiple ways over time. Juno could compare visible cloud patterns, microwave data, and gravity effects. Hubble could track long-term changes in size, wind structure, and oscillation. JWST could add thermal and composition information. A short-lived storm on Jupiter would not give you that kind of layered data set. It would come and go too quickly, or be too small or too poorly measured. The Great Red Spot is different. It stays around long enough to revisit, but it also changes enough to reveal the processes shaping it. That makes it unusually useful scientifically. In a way, the storm acts like a built-in atmospheric experiment. It is stable enough to monitor over years and decades, but dynamic enough to show how Jupiter's atmosphere actually behaves. That is a very powerful combination. If the storm were too chaotic, it would be hard to compare data across time. If it were too rigid, it would reveal less about the underlying physics. Instead, the Great Red Spot sits in the middle. It persists, but it evolves. That lets NASA keep testing new ideas against the same feature, while also learning how Jupiter changes. And that is where the storm has to be connected back to the rest of the planet, because the Great Red Spot is not isolated from Jupiter's larger atmospheric system. NASA's work on Jupiter's 3D atmosphere emphasized that the colourful belts and zones are not just decoration. They are signs of deeper processes below the clouds. The Great Red Spot sits inside that same framework. It exists in the same banded atmosphere, between the same large jet streams, above the same deep pressure layers, and inside the same giant planet circulation system. So if the spot is deep, then it becomes reasonable to ask how deep the surrounding flows are too. If the spot has a layered thermal structure, then what does that imply about nearby belts and zones? If the spot shows a link between visible clouds and deeper mass structure, then similar links may exist elsewhere in Jupiter's atmosphere. That is why the storm is not the exception to the system. It is one of the clearest windows into the system. The Great Red Spot helps scientists test the rules Jupiter's atmosphere follows. It gives them a large, persistent, measurable structure where they can compare visible appearance, chemical distribution, heat structure, pressure layers, and motion. That makes it one of the best places on Jupiter to connect the top of the atmosphere to the layers below. And that matters beyond Jupiter too, even without exaggerating the point. Giant planets are common in the universe. We know that from the broader picture of planetary science. But Jupiter is the only giant planet whose atmosphere NASA can study at this level of detail. With repeated spacecraft passes, long-term Hubble monitoring, and infrared and spectral support from other observatories. So every time NASA sharpens the picture of the Great Red Spot, whether it is the depth, the chemistry, the oscillation cycle, or the wind changes, it improves the general physical language scientists use for giant planet atmospheres. That does not mean every giant planet works exactly like Jupiter. It means Jupiter is the nearest and best tested laboratory for this kind of atmospheric physics. So the Great Red Spot is not just an answer, it is also a tool. By decoding this one storm, NASA gets a deeper handle on Jupiter's belts, zones, cloud chemistry, vertical layering, energy transport, and vortex physics. The storm became a way to test how the whole atmosphere works. That is the real payoff of this section. The Great Red Spot stopped being just a curiosity and became one of the best laboratories in planetary meteorology. A red oval people used to treat like a symbol turned into a measuring device for a giant planet. And once the storm becomes a tool instead of just a mystery, the next twist gets even sharper, because NASA and other researchers started realizing that even the storm's biography may be wrong, and the Great Red Spot people think they know may not be the exact same one earlier astronomers were seeing centuries ago. The Great Red Spot may be younger than people thought, and that changes more than the history, it changes the science too. For a long time, the easy version of the story was that the exact same storm had been sitting on Jupiter since the 1600s. People would mention Giovanni Cassini seeing a spot in 1665, and then jump straight to the modern Great Red Spot as if it were one unbroken object with one continuous life. But a 2024 study changed that picture in a serious way. The study argued that the present Great Red Spot is likely not the same spot Cassini saw in 1665, and that the modern vortex may have formed later through an instability in Jupiter's powerful atmospheric winds. That is a major correction, because it does not say the old observers were wrong to see a spot. It says continuity of location is not the same thing as continuity of identity. In other words, there may have been a prominent spot in that region centuries ago, but that does not automatically mean the modern Great Red Spot is the exact same vortex. The current interpretation is more careful than the legend. Jupiter may have produced more than one major long-lived vortex in roughly the same zone over time. So what do scientists think now? Because this is where the mythology gets replaced by something more precise. The newer interpretation says the current Great Red Spot has likely lasted for at least about 190 years, not securely for more than 350 years as the older popular story suggested. That still makes it extraordinary. A storm lasting around 190 years is already far beyond anything people experience on Earth. But it is a different problem from a single unbroken storm surviving since the 17th century. The better modern version is that Jupiter's atmosphere can generate and maintain very long-lived giant vortices, and the Great Red Spot we know today is one especially successful example. And this is not just a historical detail, it matters scientifically. If the current Great Red Spot formed in the 19th century rather than the 17th, then its shrinkage, drift, and structural evolution belong to a shorter life cycle than many people assumed. That changes the constraints on how giant vortices form, how long they can remain coherent, and what physical mechanisms can build one in the first place. A storm that is around 190 years old is still astonishing, but it is not the same modelling problem as a 350-year-old storm that never broke identity. There is also a useful tension here with NASA's broader public phrasing. NASA's current Jupiter facts material still says the Great Red Spot has been observed for more than 300 years. That is fair if you're talking about the long observational tradition of a red spot-like feature in that region of Jupiter. But the 2024 work warns that this does not necessarily prove the present vortex is the same exact object Cassini described. So the careful version is this. Astronomers have watched a great red spot-like feature for centuries, but the modern Great Red Spot may not be identical to the one seen in the 1600s. That is why this section hits so hard. NASA and allied researchers did not just revise the storm's depth, wind behaviour and stability. They may have revised its biography too. The Great Red Spot may still be ancient by human standards, but not nearly as ancient in its present form as popular culture keeps repeating. The storm did not just turn out deeper and less stable than people thought. It may also be younger than its legend. And that sets up the next escalation. Because once the storm's age becomes less certain, the next question is not just how long it has lasted, but how far its influence reaches. And NASA found that the Great Red Spot may heat Jupiter's upper atmosphere far above the clouds you can actually see. The Great Red Spot does not stop at the cloud tops because NASA found that the atmosphere far above the storm is much hotter than it should, and that means the storm's influence reaches into a completely different layer of Jupiter. One of the most surprising results came from a 2016 study highlighted by NASA. Scientists found that the upper atmosphere about 800 kilometers or 500 miles above the Great Red Spot was dramatically hotter than expected, with temperatures around 1,600 Kelvin. That is a huge result because now the Great Red Spot is not just a lower atmosphere weather feature. It is connected to heating in Jupiter's upper atmosphere far above the visible clouds. That was such a shock because Jupiter already had a known heating problem. Its upper atmosphere is warmer than simple solar heating alone can explain. The Great Red Spot results suggested that at least some of that local heating could be driven from below. NASA's summary pointed to upward propagating acoustic and gravity waves generated by the storm, with those waves crashing higher up and releasing energy as heat. In other words, the Great Red Spot may not just stir clouds near its own level, it may send energy upward into the much thinner atmosphere above. That wave explanation connects a lot of the earlier findings in a very clean way. A storm that is deep, fast, vertically layered in temperature, and constantly changing at its edges is exactly the kind of system that can launch waves upward. Those waves can then travel into higher atmospheric layers and break there, dumping energy as heat. So the Great Red Spot is not just weather below with nothing happening above it. NASA's findings support the idea that it's part of a vertical energy pathway, and this result fits into a bigger Jupiter-wide problem rather than replacing it. Later work in Nature found strong evidence that Jupiter's upper atmosphere is heated on a global scale mainly by the redistribution of auroral energy. That does not cancel the Great Red Spot result. It puts it in context. Jupiter's upper atmosphere does not appear to be heated by one mechanism alone. Auroral processes seem to matter globally, while the Great Red Spot appears to be a localized lower atmosphere source that can punch heat upward above itself. So the payoff here is very direct. NASA found that the Great Red Spot is not confined to the layer where people casually place clouds. It can influence the atmosphere high above it, likely through wave-driven heating, creating a thermal anomaly hundreds of degrees hotter than nearby regions. The storm turned out not just wider and deeper than expected, but taller in influence too, and that sets up the final section perfectly. Because once the storm turns out to be deep, layered, unstable, chemically active, historically less certain, and able to heat the atmosphere above itself, the obvious question is what NASA really found overall. and why this storm is more dangerous to old ideas than it is to Jupiter. What NASA really found in the Great Red Spot was not one surprise. It was a full breakdown of the simple story people had been repeating for years. The old version was easy. A giant red storm sitting on Jupiter for centuries, slowly spinning, dramatic to look at, but basically understood. That version does not survive contact with the data. NASA found that the Great Red Spot is deep, reaching roughly 350 to 500 kilometers below the cloud tops, about 220 to 300 miles. NASA found that it is chemically layered, with cloud decks below and a red haze above that is likely connected to sunlight-driven chemistry in the upper atmosphere. NASA found that it is dynamically unstable in ways scientists can now measure, with a long-term shrinkage trend, changing wind behavior, flaking at the borders, and an oscillation cycle seen over about 90 days. And on top of all that, newer work suggests the present vortex may not even be as old in its current form as the legend says. That is not one discovery, that is a full rewrite. So if you want the cleanest ending, it comes down to 3 myths NASA destroyed. First, the Great Red Spot is not shallow. Juno ended that idea. The storm is not just a red pattern on the cloud tops. Its roots go hundreds of kilometers down, and NASA was able to constrain that depth using both microwave sounding and gravity data. That means the visible oval is only the upper part of a deeper atmospheric structure. Second, the Great Red Spot is not perfectly stable. Hubble ended that idea. NASA and STSCI showed that the storm's outer winds sped up by as much as 8% from 2009 to 2020, and later monitoring over 90 days showed the storm changing shape through an oscillation cycle, with shifts in size, brightness, colour, and vorticity. So the storm persists, but it does not sit there unchanged. Third, the red colour probably is not some strange deep material bleeding up from Jupiter's interior. NASA's leading explanation points upward instead. The colour is most likely tied to upper atmosphere photochemistry, with sunlight acting on atmospheric ingredients like ammonia and hydrocarbons to produce a reddish, chromophore-bearing haze. That means the colour is not just decoration, it is chemistry shaped by altitude and light. Those are not small corrections. They change the Great Red Spot from iconography into physics. And the reason this still matters so much is that NASA has not solved everything. Scientists are still debating the exact composition of the chromophore that makes the storm look red. They are still working out how visible flaking at the border relates to the deeper vortex underneath. They are still trying to pin down the full life cycle of the storm, how it formed, why it lasted, why it is shrinking, and what finally happens to it. Even its biography is still being revised, with 2024 work arguing the present Great Red Spot may not be the same exact vortex seen by Cassini in 1665. For one of the best observed storms in the solar system, a surprising amount is still open. That is exactly why NASA keeps coming back. Juno's extended mission keeps refining the picture of Jupiter's deep atmosphere and internal structure. Hubble's OPAL monitoring keeps giving the time series record needed to catch changes in size, wind, and oscillation. JWST-related analysis has added sharper thermal and chemical detail. The Great Red Spot is not just something famous to look at. It is one of the best giant planet laboratories we have. Every instrument sees a different layer of the same object, and every layer keeps exposing how incomplete the old picture was. So the final point is simple. The Great Red Spot is not dangerous because it could hurt Jupiter. Jupiter barely notices it. The Great Red Spot is dangerous because it keeps destroying human assumptions. NASA went in with a famous storm and found a deep atmospheric engine, a layered chemical system, a vortex that wobbles and changes while staying alive, a local heat source that can affect the upper atmosphere, and maybe a storm that is younger in its present form than the legend claimed. The Great Red Spot did not shatter Jupiter. It shattered the old idea that giant planet weather could be explained with one easy story. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.